Okay, I'm Lia Corrales. I'm at University of Michigan, and I'm really thankful to be invited to talk about my favorite thing, which is dust features and high-resolution X-ray spectra. Okay, first I want to give people a quick crash course in interstellar dust. Um, sorry, give me 1 second, I'm having a little bit of a technical problem. There we go. Okay. So a large fraction of interstellar metals are locked up in dust grains, and this is important for a few reasons, but particularly with X-ray spectra. Metals, these heavy metals, are what contribute the most to absorption from the interstellar medium. So this little cartoon here shows you how elements in solar metals are distributed in terms of their abundance, and the red circles represent approximately how much we believe is locked up in interstellar dust grains. So you can see that a significant fraction of the metals that are actually absorbing X-rays are in solid phase. And we know this basically by looking at gas phase abundances, usually from UV and optical spectra, and then comparing that to some sort of abundance table that we assume usually somewhat solar-ish. And we see that there are some missing, and this is what we refer to as depletion. So fortunately for X-ray astronomers, interstellar dust grains are mostly transparent to X-rays. There are a few caveats if you have large grains, so let's say 0.3 microns, that's on the large end for dust grain size distributions. You do have this effect, which is sometimes referred to as self-blanketing. And essentially what that means is that the dust grain is so large that the X-rays aren't actually able to penetrate the entire grain. So you actually get a reduction in the photoabsorption effect because you're not probing all of the metal that's locked up in the solid phase. So this particular effect was talked about in Wilms et al. 2000, and just to point out in this plot, this is the ISM absorptivity as a function of energy, and this particular plot has been multiplied by E cubed to make it a little bit flat, and you can see each step up in absorption has to do with photoelectric absorption from individual elements in the ISM, and the dashed lines in this plot show the self-blanketing effect of about 0.3 micron grains, and you can see that it's noticeable, but it's not a huge effect. And for this reason, people have tended to ignore dust grains, I think, in the X-rays, or at least not worry too much about it and only use absorption models. And I just want to point out that this 0.3 microns tends to be the upper limit of most dust grain size distributions that people consider for the interstellar medium. Okay, but unfortunately, and especially as we have gotten to get nicer telescopes in space, we're starting to think about dust scattering. So dust in the ISM also scatters X-ray light, and going back to some fundamental astrophysics, really this extinction effect is the combination of absorption and scattering. So Bruce Drain wrote a paper in 2003 talking a little bit about this from the X-ray perspective, and this plot is just very nice because it shows you the gas phase absorption of the ISM, and then the dust phase extinction, which is the absorption plus scattering, and it also shows just the scattering portion. But you can see that around just a few keV, where people might start to ignore dust, you actually have to worry a lot about this scattering effect. So now I'm going to give a quick crash course in dust scattering. So again, these dust scattering particles, when they're between us and an X-ray source, they tend to scatter over small angles. So we use the variable A to represent the grain radius. And then I use the sigma tilde to represent the general scattering angle for this effect. And it's usually pretty small, just a few arc minutes. And because most of our field of view on our telescopes are on the arc minute scale, you end up seeing what we call a dust scattering halo. So an example of a dust scattering halo is here on the right. This is a soft gamma ray repeater that went out into outburst in the X-ray and then got dim again. And as the X-ray light propagated through the interstellar medium, it hit different dust clouds, and each dust cloud produces a ring in this particular echo. If you have a more constant source, or a source that doesn't have a huge outburst and then a dim again, you get a more smooth distribution in the dust scattering halo. So these dust scattering halo surface brightness profiles give us a lot of diagnostics for dust in the interstellar medium because of the small angle scattering. It's highly dependent on the grain size as well as the energy. And I'll talk about that more in a second. And in particular, dust scattering is also strongly sensitive to the grain size. So when you look at X-ray approximations for dust scattering, the scattering cross-section is typically dependent on the grain size to the fourth power, and then it falls off very quickly with energy. So when you're trying to take dust scattering into effect, when you're examining the spectrum of a source, you basically are completely reliant on the shape of the dust scattering halo. And again, this halo shape depends on a number of factors. One of them is grain size. So using the formula from before, as you go to larger grain sizes, you get smaller and smaller scattering halos. It also depends on the location of the dust. So we typically use this X parameter to quantify where the dust is between us and the source. So if you take the distance to the dust scattering cloud divided by the distance to the X-ray point source, you have some value between 0 and 1, where something closer to 0 is very close to us, something far away and close to 1 is close to the X-ray source. So as you're looking at dust that's further away along our line of sight, the dust scattering halo also gets smaller. And finally, as I mentioned before, it also gets more compact with photon energy. And when you think about it, you know, observationally, your telescope has a particular point spread function size or a typical aperture size that you might use to extract the spectrum. And if you plop down that region, you'll quickly see that in some cases, the dust scattering halo or the dust scattering effect is removing light from your point source aperture. And in other cases, it's not, because your point source aperture completely encloses the dust scattering effect. So Chris did mention this previously in his talk, but basically this gives us a slightly complicated situation where not only does the dust scattering component to extinction depend on a variety of physical parameters, it also depends on our telescope. So most of this talk comes from my 2016 paper where I evaluated this effect and some of the systematic effects that it puts on us. And so this plot is very busy. I will try to spend a few minutes explaining it, but basically what it is quantifying the fraction of the scattering halo that you're recapturing within a spectrum extraction region or aperture of a particular size. So the x-axis is the energy for the scattering halo. And as you might recall, the scattering halo gets more compact with energy. And then the y-axis is the enclosed fraction. So we're going from 1% to fully enclosing the entire dust scattering halo. So I tried a few different a few different distributions of dust along the line of sight. So the thick lines correspond to just uniformly distributed dust, and the less thick lines, solid lines, correspond to a single dust cloud, or what I call a screen, which is about halfway between us and the source. So that quantifies how much this enclosed fraction changes. And I chose a 60 arcsecond aperture for something like NuSTAR or other very low resolution telescopes. And you can see that, yeah, you capture on the order of 20% of the scattering halo to more, so that the effect is much less important. Although there are people, Kristen Madsen, for instance, who have seen the effects of dust scattering on NuSTAR. And then something like Chandra, and actually Chandra is a little bit better than this, you might use an extraction region that's, let's say, 2.5 arcseconds in radius, in which case you're capturing less than 10% of the scattering halo back. And again, that's very energy dependent. The dashed lines that are in this particular plot are talking about an XSPEC model called DUST, which is a very, very simple first approximation to trying to incorporate dust scattering halos effects. So I just wanted to show that while it's a good start, If you really want to do it right, you need to calculate these enclosed fractions to more detail. So how is this X-ray scattering effect going to affect your science? So in my 2016 paper, I just did a quick test where I simulated data sets with dust and without dust from a variety of ISM obscuring fractions. And then I fit both of those models without dust. So you can think of the red curves in the upper plot as sort of a control group because it's trying to quantify like the statistical uncertainty and Poisson uncertainty. I used a variety of fluxes and things like that. And really the biggest effect that it has is just on your measured ISM column. So on the left plot, you can see that the measured ISM column, when you do have dust in the way and you fit it without dust, you're gonna get a larger ISM column than is real by about like 30 to 40%. So that may not be a big deal to most people, and that's okay. I would just like to point out that I've seen arguments where people measure an ISM column and then they give it a distance, or they put it in, they put the source, into context as to whether it's in front of or behind another source that's based on this ISM column. So I do want people to be careful with that. It also can affect the power law that you measure from a data set, or even the flux that you measure from a data set. Usually it's going to be less than the 10% level, but I would just like to point out on the x-axis here that a lot of galactic X-ray binaries are in the like log NH 22.5 range, so it is a measurable effect. And so it really depends on the level of precision that you're seeking. And I also want to give a plug for the Smith 2016 paper, which I'm on, that also goes into a little bit more detail about how dust scattering affects the physics that you get out for a few particular cases. And again, in this particular table, we have a fit to GRS 1758. And again, it's mostly the ISM column that's affected, and you can see it's on the 30%-ish level. But there's one or two other parameters that get affected by quite a lot. So that's a good paper to go to if you want to see more specific details in terms of science. And so I do want to talk about high resolution spectra. So in addition to just overall affecting your continuum fit, high resolution of spectra around photoabsorption features are affected by this scattering component. And Chris talked a little bit about this. But here you see a graphite and a silicate grain model, and the optical depth per 10 to the 22 hydrogen column as a function of energy. And you can see that the absorption component, which is in a dashed line, is actually comparable in many cases or less than the scattering component, which is the dotted line here. So I'm going to zoom in on the iron L shell photoabsorption region, and you can see once again, basically what happens, and again, Fritz mentioned this, when you have an absorption feature, that resonance also affects the scattering cross-section. And so what you end up having is a little bit of a lip at the low energy or long wavelength side of the photoabsorption feature. So this little dip in the scattering cross-section causes also a dip in the overall extinction cross-section. So this effect, it's basic physics, so it's been known for a while. And there's some other papers that talk a little bit about it. But because the absorption and scattering components are approximately the same, if we don't include both of them, you're first probably not gonna, you're gonna overestimate your ISM column or your iron column or whatever it is that you're interested in. And then you're not gonna fit the high resolution features as well. So I give examples of that in the example case, which I'll go through in a bit. And then of course, this fine structure, which I'm starting to label now X-ray scattering fine structure because it's just faster to talk about. So the appearance of the scattering fine structure also depends on your scattering halo shape and telescope imaging resolution. So to demonstrate that, on the left, I show the iron L shell that you saw before, which is computed with an MRN distribution. So that distribution I was talking about earlier that cuts off at 0.3 microns in terms of grain size. And I calculated the dust scattering halo for, I believe it was a uniform case. I can't remember right now, that's okay. But I use a 10 arcsecond aperture and a 60 arcsecond aperture for my telescope's region size. And you can see there's, you know, maybe a 10 or 20% effect. But if you go to larger grains, which actually have a lot more scattering, you also have a more compact halo. As I was mentioning earlier, the scattering halo size gets smaller when you get to larger grains. So when you look at this extreme case of only 0.3 micron grains in the ISM, you can see that the 60 arcsecond aperture catches something like 20 or 30% of the scattering halo. And so your features actually get reduced. The other thing I want to point out is when you get to larger dust grains, that you can see that self-blanketing term, or that self-blanketing effect coming out in the absorption cross-section. So when you have the smaller dust grains, you get a larger absorption effect, and when you only look at the large dust grains, the absorption is reduced, but the scattering is increased. So you get these very different looking extinction cross-sections. And there has been evidence seen in the interstellar medium for this effect. Basically, when you have that reduction in the extinction cross-section, or that reduction in scattering near the absorption peak, you get something, and you fold that through as extinction, you actually end up with something that looks almost like apparent emission, or an emission peak. So this is from Ziegers et al. Paper of the low mass X-ray binary GX5-1, and they argue for the existence of larger dust grains around 0.5 microns, and they fit the silicon edge with that particular model. Okay, so in this paper, I took the Drain 2003 optical constants with MRN sizes, and I computed a really simple model to release to the astrophysical community just for the simplest cases. So this particular model, ISM dust, is absorption plus scattering. It's literally those two things added together, which means that it's really intended for high resolution telescopes, high imaging resolution, so really Chandra and XMM Newton. It includes the X-ray scattering fine structure. And I would say that it's totally good enough if you care about doing continuum science. So if you care about the science that you're extracting from your continuum measurements and you want a certain level of precision, this is fine. If your science goal is astromineralogy, or some, I would say even ISM abundance measurements, I would use direct lab measurements. So there's some becoming available now from Esron, and then there's some from Julia Lee from about 10 years ago. So if you want to do astromineralogy, don't use this model. But if you just care about continuum, it's fine. If you're working with low imaging resolution telescopes, or you just want to use you want to try out different dust model settings, use XSCAT, which was released with the Smith et al. Paper in 2016. And I'll talk a little bit more about that in a second. Okay, so on the website, I linked to a Google Doc that is an exercise in applying the ISM dust model. And we start with a continuum fit to GX9+9, which is one of the sources that I put in my 2016 paper. So we're basically just reproducing some of the work that I did for that paper. I put my solution online on Zenodo. So if you go to this URL at the top, you'll be able to download this presentation, the exercise instructions, and then a Python script that I use to just try it out. I actually learned PyXspec for this exercise because I thought it might be easiest for people who are new to the field to work with PyXspec, since it already comes with Helisoft and you don't have to install anything extra. I used Python 3, Helisoft version 6.27, and then I throw in a little bit of AstroPy and some other things, which are definitely not necessary to complete. But this is the spectrum as observed in TGCat, and I have instructions for downloading it. And here I am setting a continuum model, which is just a power law with ISM absorption and then ISM dust. So TB VARABS, I don't know what to call it, is the Wilms et al. Model. And it can actually be quite overwhelming because it has a lot of parameters, so I will go through those. By turning on both ISM absorption and dust scattering or dust extinction effects, you have to make sure that you're not accidentally counting the dust twice, because TB VARABS also includes dust. So I apologize, it's very small, but here's actually all the parameters of that model that I just defined. There's a power law, and then the TB VARABS model has, I use VARABS because I want to be able to change some of the abundances in the model, rather than just TBABS, which just includes the hydrogen column density. So the first set of 17 parameters here corresponds to the abundance relative to whatever. Okay. And then you have the dust model parameters, the gas fraction, and then I put ISM dust there. And we just leave redshift at 0 because we're talking about local extinction. I tend to go to table 2 of the Wilms paper to set the abundances. So the Wilm abundance model, when you set it in XSpec, will set it to these values in the table. And then you can look at this 1 minus beta parameter, which basically gives you the gas phase fraction. And so the point is that you want to set your TB VARABS abundances equal to the gas phase fraction. And sorry, oh, I'll show it in a second. So here I am doing that. I'm setting the just the abundance models. And then finally, what I do is I tie my ISM dust parameters to the NH column. So I have to assume a particular dust to gas mass ratio for the Milky Way. That's typically 0.01. And in this particular example, I just take this 10 to the 22 NH column times, a proton mass times 0.01 divided by the units of the dust mass column that I use in ISM dust, which is 10 to the minus 4 grams per centimeter squared. So this will show you how to do it in Python. And so here's what my fit will look like before I actually perform it. You can see that the abundance, the elemental abundances have changed. For some reason, the default in XSpec is to have the gas fraction set to 1, so I actually don't have to touch those, but definitely check them. They should all be set to 1 before you run this. And then here's the results of my fit. This particular low mass X-ray binary has some emission components, so power law is not really the best physical description of it, but it generally works. I just want to point out that the NH column you get if you were to just do a power law times, let's say, pH-abs, which a lot of people use for ISM absorption, you get a different NH value, a different normalization by like 10% or so, and not much else changes. So again, it depends on the precision that you want, but if you're looking for 10% precision, definitely worry about dust. Okay, so I'll just go through some quick fits that I did to, like local fits just to iron L. Here I do a fit to using an edge model, which is the simplest model you get for photoabsorption. It's just a step function. So this is where we see L shell absorption. It does okay. Also, I've binned this data by a lot just for visual purposes, so I recommend checking it out with less binning. But you'll see as I step through different models, it gets a lot better. Here I do ISM abs, which actually uses pure metallic iron L shell absorption, so it's not a gas phase cross section, but it doesn't include dust scattering or anything like that. You can see it does all right. And then when I do ISM dust, which includes scattering, you can see that that little emission peak near the absorption edge goes up, and the residuals actually get a little better. So I'm going to step through it really quick so you can see them all in succession. So here's the edge model, here's the ISM abs model, and then here's the ISM dust model. So I would say there's still a lot of structure around the photoelectric absorption edge that could be due to astromineralogy effects, so X-ray absorption, fine structure, but in general, on the low energy side, you get a better fit. Okay.
30 seconds.
Great. When to worry about dust and dust scattering? Where is your dust? If it's intrinsic to your source, don't worry about it. You can just use absorption. If it's not, so usually Milky Way dust, use dust scattering. I like to use this diagnostic for whether or not I should include it. Take your scattering optical depth, multiply it by 1 minus your enclosed fraction. So if you're enclosing all of the halo, doesn't matter. You don't need to include it. But you can read off of this plot whether or not to include it. So my example of the iron 6.7 iron line complex 10 to the 23. So let's say galactic center source observed with SWIFT, it's a 10% effect. If you're worried about larger dust grains, again, if it's intrinsic to the source, just use absorption. I would recommend TB Varabs so you can play with dust parameters, or use XSCAT, which extends to larger grain sizes than ISM dust does. I just wanted to make a plug for this recent paper by Ralph Bauhausen. You also could worry about dust fluorescence. So check out that paper if you're worried about dust that's intrinsic to your source. I have a GitHub model that you can use to calculate your absorption and extinction cross sections. Collaboration is welcome. And I'll stop here and take questions.
Thank you. We have time for 2 quick questions. And I apologize for the large number of parameters in TBVAR ups. Sorry. So there's one question in the chat that was on by Adam Stone. Does this affect, I guess, of trying to constrain metal abundances in something like supernova remnants? Oh, does this affect trying to constrain metal abundances in something like supernova remnants?
My understanding is that the metal abundances you're looking at probably come from hotter phases. So I would say in general, no, but if you're noticing, or if you want to, let's say, probe dust in a supernova remnant, I would use dust absorption only because the covering fraction is rather high. And again, anytime you want to look at the solid phase, I would recommend using lab cross sections if the solid phase is your science goal. Because the abundance that you measure is going to depend on the mineralogy of the dust that you're able to probe with X-rays.
Okay, and a quick comment by Chris. In XSpec, I can see ISM apps, but not ISM dust. Is it called something else?
You probably have an older version of XSpec. I think it was incorporated in XSpec around version like 2.5 or so, but probably Keith Arnaud could answer that question better than me.